Hello students, welcome back. Let's begin an actual implementation of Frobenius method. Here's a reminder. This is a general form of Frobenius series, and we're going to take the derivatives term by term from here and plug those into this original. And first we find out R, and then we find out Cn. Okay, here we go. The first problem. Ready? Okay, all right. The given ODE has a regular singularity at t equal to 0, and we're going to use Frobenius method from there. All right. Frobenius series, the derivative, and the second derivative. Is everybody happy with that? Power comes out as coefficient and subtracting 1 from the power, and then another power, subtract another 1 from the power. All right, let's put all these into the original equation here. So y double prime will be this one, and then y prime will be that one, and then y is going to be this one. Well, I can plug those in and then break up too, but I guess it's going to be a bit easier to break up first and then plug it in. Okay, all right, let's do that. Break up the parentheses like these. The middle part is broken up. And then let's bring in y double prime as this. And then y prime is this. And then y is going to be the original Frobenius series. Oh, this 2 is going to be blue. Do you see it? That's y double prime. And that's y prime. And y prime again. And then that's just y. Color coding helps. Next, I'm going to slip in this t squared in. And this t squared here and minus 2 will collide and they're going to cancel each other out. This t and this minus 1, they're going to cancel each other out. This t squared and this minus 1 will not completely cancel each other out. We're going to get plus 1, like this. Okay, so this is what we got from the red series. And then this is blue. And then like this. Now I kind of regret using blue for both of these two. Originally they came from this y prime, so I used blue for this one and that one as well. But now I'm focusing upon from transition from here to there. So let's use something different here. Shall I make it bold? Okay, all right. So pay attention to this bold part. Minus 1 power became plus 1 power. That's because multiplied by t squared. And the others all became t to the n plus r power. So they're all okay, except for the last one. So let's take some index shifting and make everything into t to the n plus r power. Okay, this one's okay. That's okay. That too is okay. This one needs some work. How do you do that? Okay, all right. So from here, and I don't need bold anymore. And then I don't need different color anymore. From here, I have to get this into n plus r power. So I need n minus 1 plus r plus 1 so that this whole thing becomes n plus r power. Let me expand the font. So what did I do? I inserted n minus 1 in place of n. So I have to do the same thing in other places as well. All right. And then one more step. Let's see. And it's now starting from 1 to infinity. So that's gonna take place right over here. And here, n minus 1 plus r plus 1. So we are gonna get what we want, n plus r power. So this both part will become like this. And the other three are okay as they are. N plus r power, n plus r power, n plus r power. No problem there. All right? So here's the conclusion. N plus r power, n plus r power, n plus r power, no problem. This one, we just worked out. Highlighted in bold. Okay, now that we got all the index shifting and everything done, and everything is in terms of t to the n plus r power, I can put all those together. For ordinary points, I could simply put everything together starting from n equals to 0, because virtually there was no difference whether I start from n equals to 1 or n equals to 0. The difference was just adding another 0. Consequently, no difference. This is different this time. If I plug in n equals to 0 here, if this is 0, we have r minus 1. Instead of just 0, we have r minus 1. So we are adding something non-zero. We need some work. So how do we do that? We have to consider n equals to 0 case and n is greater than or equal to 1 case separately. When n equals to 0, only these three series contribute, and this both series does not. And when n is greater than or equal to 1, all four series contribute. Let's consider n equals to 0 case first, and from there, we'll end up identifying the r value. Here we go. Plug in n equals to 0. Okay, all right. A bit too much. So, okay, all right. Let's plug in n equals to 0 here. So 2 times 0 plus r, and then 0 plus r minus 1, and then c0, and t to the r power. Okay, 0 plus r, so r power. And how about this one? Plug in n equals to 0, so 3, and then n equals to 0, so r, and c0, and t to the r power. And this one does not contribute because I begin from n equals to 1, so the series here, c0, t to the r power, and they have to add up to 0 because everything has to be 0. And then of course t to the r power, they're all common, cross all those out, and then c0, that's common, so take it out. What do you get? 2r squared minus 2r. Did I break up correctly? And then plus 3r, and then minus 1. So what do you have? 2r squared plus r minus 1. Is that what I'm getting? Is that what I'm getting when I'm plugging in n equals to 0? Indeed. That's what I'm getting. So from here, factor c0 out, You see, t to the r power is going to be cancelled out anyway, so I didn't bother writing all those. Factor c0 out, then we have 2r squared minus 2r plus 3r minus 1 equals to 0. C0, and then we have 2r squared plus r minus 1 equals to 0. And what further conclusion can I draw? C0 times 2r minus 1 r plus 1 equals to 0. Did I factor correctly? Plus 2 minus 1, yeah, I guess that's right. So C naught is equal to 0, or r is equal to 1/2, or r is equal to -1. That's what I'm getting. Are you with me here? Let's have a brief recap. Frobenius series, first derivative, second derivative, all right? And plug all those into the original equation. And it's a bit more convenient after breaking up, so let's break up first. You could plug in and then break up later, but breaking up first is a bit more convenient. And then plug all those in. All right, and then power computation, second power, first power, and second power, this minus 1 power, and so on. We get the simplified form, and then we need index shifting. We need t to the n plus r power for all those things. These three series are okay. This one bold. That one needs some work, and once you do some work here, you're going to get this through index shifting. And then you're going to plug in n equals to 0, and then n greater than equal to 1 separately. N equal to 0, then this one doesn't contribute, and we have only these three series. It's this one, but it's repeated down here, so let me just go down here. I didn't bother writing t to the r power there. They're all common, so what's the point? And then factor those out, and then C0 factored out, and then what's left is a quadratic expression of r. The factored further, we get either r is 1/2 or r is -1. When C0 is equal to 0, you're going to get just all 0, and you'll see later, but this is not going to be really interesting. And you see, what you need is two linearly independent solutions, right? And we have two r values. And plug in those two different r values here, 1/2 or -1, you're going to get two Frobenius series. And they're going to give you two linearly independent solutions. So this one or that one, you'll have to consider separately later. Now what if n is greater than or equal to 1? In that case, all four series contribute. And this is what we get. First series, second series, third series, and fourth series. This one came from this here. And then you can solve for Cn. So from here, you can solve Cn is some expression of r times Cn minus 1. You can get a recursive expression like this. And what expression goes here? That's going to be a bit of an interesting, and it's going to be a bit of a work as well, a little bit tedious work. But once you get that, you're going to get a recursive equation. So from C0, you're going to get C1. And then from C1, you're going to get C2. And from that C2, you're going to get C3 and so on. Here's a computation. Okay, we already discussed that. From r equals to 0, we get r equals 1/2 and r equals -1, okay? All right, for n is greater than or equal to 1, okay, we get this recursive equation. And when r is 1/2, this case, plug in 1/2 over here, r is 1/2, and then solve for Cn. And we're gonna get something like this. Oh boy. As a matter of fact, you can use Mathematica command to find out Cn in terms of Cn minus 1 like this. And eventually you're gonna get this expression. It's a bit tedious work, but take my word for it. And then in practice, you just plug in appropriate value, start with arbitrary C0 and then get C1, some number times C0, and then do it again, some number times C0, some number times 0, 0, and 2 or 3 times, and then you just move on. But here, in this particular case, the question was so simple that it is possible to find appropriate pattern. This is rare. In reality, you're not going to get these. Just some numbers, and then you just move on. Some numbers, and then you just go over to this expression where this r is 1/2, and that's about it. But in this particular case, you can get everything. And r equals to -1, again the same deal. Plug in r equals to -1, and solve for Cn. Tedious computation, so I use Mathematica to solve it. And we got that. And in practice, you just plug in some numbers. So C1 is some number times C0. C2 is some number times C0, like that, and put 2 to 3 numbers, and then just go back to this Frobenius series, and r equals to -1, and that's going to be your y2. And in the end, you have linear combination of y1 and y2, kind of like ay1 plus by2, kind of like that. But here in this case, it is possible to find pattern, and this pattern wasn't too bad because you're going to end up with 0 and then all 0 later on. So Cn is like this for r equals 1/2 case, and we have first 2 numbers and all 0 for r equals -1 case. So we have first Frobenius series and the second Frobenius series, like that. Now I'm using the same C0, C1, C2 for both of those series, so they can be a bit confusing. So let me change those into capital A and capital B. And you're going to get like this. And here goes the general form. But please be warned, this kind of general form here is one of the rare case. Most of the time, you're going to get an answer that looks like this. Y of t is a times the Frobenius series. Where is it? Here we go. B times the Frobenius series, and that's -1. And then of course, I cannot use same Cn's here because they're going to be different. So I need another character. Like this. And then we have An is equal to first 2 or 3 numbers and ... And Bn, again, first 2 or 3 numbers and ... That's about it. Most of the time, you cannot find pattern, and that's going to be waste of your time. Most of the time, you just write like this. And yes, this is very important. R value for 1/2. Let me emphasize it in bold blue. And let me emphasize this one in bold red. Because by plugging in n equals to 0, you found out those two. But in the end, A and B and those are just first several terms, and that's about it.